what I want to do is to describe a little bit about some work that Stephen Hawking, Andy Strominger and myself have been doing recently in an attempt to solve the information paradox. But perhaps I should start off by saying what exactly the information paradox is. So the idea is that you can form black holes sitting in space-time. Eventually they will evaporate through the Hawking effect and disappear. At least that appears to be the simplest possible scenario associated with the Hawking effect. So the kind of idea that you have, if I draw something like a Penrose diagram that describes this kind of process, you have a picture that looks like this. So this object here would be a collapsing star. As it collapses, it will eventually form an event horizon. That's a surface that looks like this. It will eventually evaporate, leaving you with space-time up here, which looks more or less like Minkowski space. And down here, things look more like Minkowski space. The evaporation process comes about because the black hole will have a temperature of approximately 1/8 pi times its mass. This is written in natural units. And therefore, what will happen is that it will radiate particles more or less at a rate given by the area of the horizon, the area of the black hole, times t to the fourth, simply the Stefan-Boltzmann law. This thing will look like the mass squared of the black hole, and the whole thing looks more or less like 1/m squared. So that means that you would expect, assuming that this formula is universally valid, the black hole will live more or less a lifetime that looks like t to the m cubed. For most astrophysical black holes, this time is enormous. So for one solar mass, this timescale will be the order of 10 to the 58 Hubble times. So for practical purposes, you don't really have to worry about this. But what you do have to worry about is matters of principle here. The situation that I've described, in some sense, violates the laws of quantum mechanics. It's easy to see why. Down here, we could define an initial state. It would be described by some incoming density matrix, rho I. Up here, we could have a final state described by some outgoing density matrix, rho F. And in quantum mechanics, you'd expect a linear map between the two, and you'd expect something like a formula rho F equals some object, which I'll call $, acting on rho I. In quantum mechanics, this object $, has to factorize. So that $, will be equal to something like S dagger S, where S is the usual kind of S matrix. That's because you would expect there to be unitary time evolution between the initial and final state. That's what happens in quantum mechanics. The Hamiltonian, a self-adjoint operator, generates time translations. So you'd expect this initial state here to evolve into a final state up there that was unitarily related to each other. Well, that much is kind of simple. The real question is, what has gone wrong? Why is this an unsatisfactory picture? The real reason is because when you look at a black hole, that's this region of space-time, what has happened is that lots of stuff has fallen into it, but you have absolutely no idea, if you're sitting out, say at some point in space-time here, you have no way of knowing what has fallen into it other than by observing what happens down here. So if you're on a surface like this, you will be faced with some kind of problem about how to describe the situation. The real reason is that black holes are essentially unique. You can't tell the difference between a black hole that is made of old television sets or an old star or me. They are independent, or at least so we believe, largely, on their method of formation. If you want to describe the black hole as an isolated object, which simply sits in space-time, then it's specified entirely by a small number of parameters: the mass, its angular momentum, and its electric charge. You could imagine some slightly different scenarios in which there were more gauge fields than just the electromagnetism, but it doesn't change the basic idea that at least from the point of view of static black holes, that's all you need to describe them. I guess I should say of static black holes. So if you're sitting in the middle of this space-time, say for example on this surface here, if you ask yourself what characterizes the black hole, the answer is its mass, its angular momentum and its charge, and nothing else. But if you're down here, you would say what characterizes the nature of gravitational collapse. You would have all of the information about the star that is undergoing collapse or whatever other object is doing it. If you're up here, what would you see? Well, what you would see is just simply the radiation caused by the fact that the black hole is hot. We have a formula here. We had a formula here at any rate. We're told that the temperature is 1 over 8 pi m.
Malcolm, you mean stationary, right? Because of the
Yes, okay. We're told that the temperature is 1 over 8 pi m. So all you would see up here is the radiation from the black hole. It does independent of the way in which it is formed, the black hole is formed. This radiation will appear simply precisely Planckian. So that's the conventional scenario in which you don't really see how you can manage to make that consistent with quantum mechanics. Quantum mechanics demands unitary time evolution, but somehow the presence of the black hole has erased all of the quantum mechanical information associated with this system. So that's the nature of the paradox. You can't have unitary time evolution if you believe in the picture that I've just painted. Various suggestions have been made how to get around this. One, quantum mechanics breaks down. It's generally felt that that is a very unpalatable idea because quantum mechanics is extremely well tested. Even small violations of unitarity will give rise to serious issues. And perhaps the easiest way to see this would be to ask yourself, what kind of things would you expect in quantum mechanics that would happen if this kind of violation happened? The one simple thing is that Noether's theorem tells you that local symmetries I'll change that slightly. Symmetries, they don't really have to be local, are associated with conservation laws. They could be either local or global. So, for example, baryon number is an example of a global symmetry. It would be violated in this kind of process. So, for example, a black hole made of matter would be indistinguishable from a black hole made of antimatter. You wouldn't be able to tell the difference from the outside only by looking at its method of formation. If you get rid of the idea that there should be unitary time evolution, then the relationship between symmetries and conservation laws disappears. You would have no conservation, as exemplified by the baryon issue, and so you would notice all kinds of violations of conservation laws which we have not seen. The same would be true for things like energy, or momentum, or angular momentum, or charge. All of these symmetries, although they could be symmetries of a fundamental Lagrangian, would not lead to conservation laws. So one tends not to believe that scenario. There is some evidence from string theory that, at least in string theory, quantum mechanics does not break down, but you are able to have black hole formation and evaporation, but it's consistent with unitarity. I don't want to get into the details of how that could possibly work. All the calculations that have been done to date have been based on the ADS-CFT correspondence, which is a little bit beyond what we're going to do today. Possibility 2. Black holes don't evaporate completely. They leave remnants. This is really a bit of a cop-out. So the idea, instead of having a Penrose diagram that looks like an evaporating black hole sitting over there, the black hole, once formed, will stay there forever. So the Penrose diagram for a situation like that would look something like this. You would see some Hawking radiation here, but the black hole would eventually sort of cool down, dry up, because after all we know about the Hawking process is that it's a semi-classical process. So perhaps what happens when the black hole gets very small is that the Hawking formula T equals 1 over 8 pi m doesn't work anymore. The problem with that, of course, is that if you thought that all of the information about an incoming state here was contained in the black hole would have to have very small mass, but involve arbitrarily large amounts of information falling into it. So it would have to have an enormous entropy, even at small masses. And that seems somehow implausible, given everything that we know about thermodynamics. So remnants are unsatisfactory. Because small black holes must then contain arbitrarily large amounts of information. That seems implausible. A third possibility is that the radiation isn't really thermal, that you have somehow omitted some degrees of freedom of the black hole, that they've got some hidden degrees of freedom that are not usually accounted for by the black hole uniqueness theorems. radiation would only then be approximately thermal. It would be thermal at early times, so it would look thermal as far as we can tell. But at late times, when the black hole is about to disappear, all of the information would have to come out. The problem with this scenario is very simple. If you ask to look for stationary black hole spacetimes, they are very constrained. And in fact, there are a whole collection of theorems dating from approximately 1960 to 1980, which show that if you take a stationary black hole, it is only described by these three parameters. These are the content of the so-called uniqueness theorems, which were proved over a number of years by Werner Israel, David Robinson, and Stephen Hawking. So if you want to resolve this paradox, you could look at option 1 or option 2 or option 3 and decide which you're going to try and follow. What Andy Strominger and myself and Stephen Hawking have discovered is that there is a hole in what are usually called the no-hair theorems. Black holes are not as unique as you think. The flaw in the argument really comes about by asking what happens for stationary black holes. Black holes, of course, are not stationary. If we look at the Penrose diagram of things which are associated with gravitational collapse, it's a very time-dependent thing. So there is a situation that looks like this. There is gravitational collapse here. Whilst it's true that things are approximately stationary up here, outside the black hole at late times after collapse, it doesn't mean that it's always that way. What you have to do is to investigate the property of time-dependent black holes. So let's have a little digression into a piece of physics dating from the 1960s, which is usually goes by the name of BMS symmetries, standing for Bondi, Metzner, and Sachs. These are symmetries of any asymptotically flat space-time. But instead of looking at what happens at space-like infinity, you look at what happens at null infinity. So Scri plus is the future boundary of all light rays in black hole spacetimes. When one asks for the properties of stationary black holes, what one is really doing is asking about the nature of what happens at space-like infinity. So if you have a situation like this, when you want to prove the uniqueness theorems, what you would do is not look at a situation that is dynamical and involves gravitational collapse. What you would do is to say, I'm going to look at an eternal black hole. So if it was a Schwarzschild black hole, then you would look at something like this. It's a sort of example of what you expect. You would say, because it's stationary, I may just as well look at what happens at space-like infinity. All infinities are the same. So you'd look at space-like infinity I0. You would construct a surface that looks like this, and you would say that the geometry out here was Schwarzschild or Kerr-Newman or whatever you wanted, and that specifies the geometry completely. So that's all you would need to do. What is the symmetry group at I0? Well, we know what the answer to that is. It's just going to be the Poincare group. Of course, the black hole can be characterized by its mass, angular momentum, and charge, but of course you could translate it. It could be moving, but that doesn't really bother you. Motion is part of the Poincare group. It's a symmetry of the space-time, and so you could quite happily perform a translation on the black hole and say, oh, it's the same thing as we first thought of, just moving. The same is more or less true of rotation, and the same is true of all of the generators of the Poincare group. There is a symmetry associated with it. You can act with that symmetry, and the space-time is invariant, other than the fact that you've made the black hole move. The situation at Scri plus, fusion null infinity, is really quite different. That was discovered by Bondi and Metzner and Sachs in the 1960s in really quite a fundamentally important series of papers. They were interested in the nature of gravitational radiation and what it does for you. They found that at Scri plus, there is a much bigger symmetry group called the BMS group. Scri plus is the place that you should look. After all, astronomers or physicists do not sit at space-like infinity out here. They sit at Scri. They look at the system and see how it evolves. So they'd look at light rays coming out from this region and determine the physics of what's going on by looking at those light rays. So it's really at Scri plus that you want to investigate the symmetries of the space-time. The question then amounts to, once you've got over the idea that black holes might not be quite so stationary or static as you might have thought, what are the symmetries at Scri? Because those are the ones that apply to dynamical systems where the black hole actually evolves in space-time. So what are the symmetries at Scri plus? The easiest way to see this is to construct a set of coordinates in any asymptotically flat space-time. First of all, one constructs a retarded time coordinate which goes up Scri. Let's call that u for retarded time. And if you constructed the metric of this space-time, you'd start off by saying it was something like ds squared is equal to minus du squared minus 2 du dr plus r squared times the metric on a unit 2 sphere. I'm going to write that in complex coordinates because it makes life a little bit easier. This is metric on the But of course, we all know that there will be corrections to that. This is just the metric on flat space. So the corrections to it, I'll write out a few of them. It starts off with a term which looks like 2mb over r du squared. This basically tells you about the mass of the system, but mb is going to be, in general, a function of the complex coordinates on the 2 sphere. It represents the Bondi mass of the space-time, and to all intents and purposes, it is the mass that you would measure gravitationally if you sat at Scri plus and asked yourself, what is the gravitational mass that you would observe sitting up at Scri plus? There are more terms. These are interesting for us. This one is subdominant. At infinity, the space-time, of course, is flat, but it contains this correction to order 1 over r. But there's some other subleading terms. This sphere at infinity could be warped slightly. So there will be a term that looks like r times czz, dz squared plus its complex conjugate. And then if you are careful and solve the Bianchi identities, you will discover there's another term that looks like, involves this thing, dz czz du dz plus its complex conjugate. And to the first subleading order, that is all you get. But, of course, there will be higher order stuff that sits here. What is the physical significance of this? Well, really what this C is doing is telling you about gravitational radiation that goes through Scri.
you say that this term with R is subleading?
Well, so this term here is got an R squared in front of it. So here we have just a factor of just an R, so it's subleading compared to this one.
The first line is just a flat Minkowski.
Yeah, yes, this is flat Minkowski space. And then this will be the first kind of Newtonian type of correction, but it also comes with some other terms here which are labelled by C. They describe gravitational radiation or mass loss from the system. We can be a bit more precise. We can look at how the mass changes as you move up Scry, and there's a nice formula that tells you about this, dmb by du. So it's how the Bondi mass changes as a function of time. It's going to be equal to 1/4 of, let's see, dz squared, I guess I'll write that dz, nzz, plus complex conjugate, minus 1/4 of nzz. Then there's a final term, plus 4 pi g T u of matter, evaluated as r goes to infinity. This tells you how the Bondi mass changes. Here, n is equal to du of czz. So what this is telling you is a formula about how the mass changes as you move up Scry. It contains essentially 3 terms. This one is a little hard to understand, but it involves the time derivative of c. But this one is easy to understand. This represents any matter that is flowing out of the system. So if you were looking near Scry, the kind of thing that can happen is that stuff will come out, matter is simply expelled from the system, and that's what this term tells you about. Then there is this term.
But this isn't necessarily defined at infinity, right?
Very good. You would have discovered what we discovered. This formula, of course, holds as in its form at infinity, but of course applies in many other places. I'll come to that in a little bit. This term here, nzz squared, represents the flux of gravitational radiation. This is matter flowing through Scry. And this is something which is related to the flux, but it requires a little bit more effort to understand precisely what it is. You should probably just think of it as being a modification to this term to make everything covariant. So a typical system will evolve in that way. Something very nice. Well, let's leave that for a moment. Now, what has that got to do with conserved quantities at infinity? If you think about what happens at I0, one of the things we talked about was the mass. It was fixed. At I0, the mass is simply the total mass of the space-time. It can't evolve because it has no time to evolve. It just simply sits there. If you want to look at the evolution of the system, you need to look at what happens at Scry plus. And what we have just seen from this formula is that the Bondi mass can change. But it changes in a way that does not affect the asymptotic symmetries of the metric. Hopefully it's down here. Asymptotically, the metric still looks like this. What Bondi, Metzner and Sachs did was to classify the symmetries of Scry plus in the same way that you classify the symmetries at I0, space-like infinity. Space-like infinity, you have the Poincare group, at Scry plus, you have the BMS group, which turns out to be the semi-direct product of what are usually called super translations with a Poincare group. So the Poincare group is familiar, so I'll forget about that bit and just look at the supertranslations. What are they? Those are going to be transformations which preserve the asymptotic form of the metric. That is to say, this bit. So leaving aside the issue of what happens with Poincare transformations, these transformations are simply a set of coordinate transformations where u, the retarded time at infinity, goes to u minus any function you like of z and z bar as long as it's real. That's just a coordinate transformation. In order to preserve the rest of the asymptotic form of the symmetries, you need to make a coordinate transformation on R, and that is R minus dz dz acting on F, and you need to make a transformation of Z, which is Z goes to Z plus 1 over R dz of F. What is this symbol dz? This is just the covariant derivative with respect to the unit 2-sphere at infinity. That's the metric given by gamma z bar over here. Under these transformations, the asymptotic form of the metric is preserved. You can now see immediately the nature of this group. This part of the group, these are the super translations. Just form an infinite dimensional abelian group because you can take one super translation, combine it with another, and they're just additive. It's the nature of functions. So super translations form an infinite dimensional abelian group.
This is special for dimensions?
In the way in which I have described it, yes, but there are analogues in higher dimensions. Please don't ask me other questions of that nature. I should say that almost everything I'm going to say is four-dimensional in nature. One hopes that, well, you'll see why that is probably not a serious restriction. So you have a whole function's worth of things as long as they're well defined on S2. Are these things, are these super translations, how do they change the space-time? Well, the easiest way to see what they do is to try to figure out what the effect of a super translation is on the metric. So we have here the metric. This term is completely invariant. However, super translation will change M Bondi, and it will change the nature of C. Those are subdominant terms, but they do not stop the space-time being asymptotically flat. A nice way of seeing this is to invent a vector field. Which generates infinitesimal transformations. That you can do, it's fairly easy. Psi is equal to f d by du. And then you have to put in some correction terms, which are plus dz dzf d by dr It doesn't look real, but actually will be. Plus a further correction term, which is minus 1 over r d squared f d by dz. Did I say that right? Plus complex conjugate. Make sure that's actually right. Yes, that's what I wrote. So these are the infinitesimal symmetries associated with BMS transformations. If you ask yourself what is going to be the Lie derivative of something like the Bondi mass with respect to this vector field, you will discover the Lie derivative with respect to psi of mb, which represents what happens if you translate through time using f. It's going to be just f times mb dot. You can ask yourself, what is the Lie derivative with respect to psi of czz? That's a bit more complicated. That's equal to f times nzz. So this represents the flux of gravitational radiation. It's sometimes called the Bondi-News function. And then there's a correction term that you need to add, which is minus 2 dz squared f. So that's how these metric parameters change. The subleading part of the metric changes. The leading part of the metric does not change. You want to regard all of these things, all of these spacetimes where you change things by a BMS transformation as different. And the easiest way to see the differences is to ask yourself, what physical things can you compute given that you make a BMS transformation? After all, BMS transformations tell you something about the flux of gravitational radiation or stuff leaving the system.
So now, just quickly, so the higher order terms beyond the first order, this takes care of those terms as well, right?
Yes. You can start doing 1 over r expansions if you like. I don't like to do that. It takes time. It's very boring. Best done with a computer. Rather opaque. So you don't want to do that. The easiest way to see what the effect of a supertranslation is and what it has got to do with radiation at infinity is to look carefully at the Einstein equations. One of the Einstein equations is dz of czz minus dz bar of cz bar z bar is equal to 0. You make sure I got all the bars in the right place. Doesn't quite look right. We need bars there and not there. That's one of the Einstein equations, and that actually tells you that because this thing is just on the sphere at infinity, that C can be written in terms of a potential. So CZZ is going to be equal to, this is basically an integrability condition for this thing, minus 2 dz squared of C. So this thing is some kind of scalar. Now let's ask ourselves a simple question about physics. What happens if you let the system evolve a little bit? So rather than do a huge calculation, let's do a simple one. Let's suppose that we have some space-time we don't really care what happens here. Let's suppose that it's stationary up to here. So up to some initial time. The system evolves, it radiates, it does something interesting, and then finishes at UF. What happens to C? Well, it's fairly easy to write down an expression for C. Under these circumstances, the change of C is going to be given by an integral over d2z prime, some horrible Green's function, which I'm not going to write out, and then an integral of something between ui and uf of, get this right, TUU minus a quarter of nz squared. So what this tells you is that the change in C is going to be some complicated thing involving a Green's function times the flux here. What you will discover, if you work a little bit harder, that this is the same as a BMS transformation. So time evolution is the same as a BMS transformation. And in fact, the object F, which describes the BMS transformation, is just simply this thing. So the evolution is described by a very simple expression. How would you see this physically? Well, there's a nice way of doing this. This is usually called gravitational memory. It was discovered by Thorne and Brzezinski when they were investigating the nature of gravitational radiation. Here's a simple example, but you can invent more complicated examples than this one. Let's suppose we are sitting at the Earth, and you constructed around it a series of inertial objects, satellites, which are in orbit around the Earth. So doing that, but maybe just moving in a circle. Suppose that you had gravitational radiation going through the system. Oh, I should say these are long distances from the Earth. Suppose you had gravitational radiation going through the system. So there would be a time at which it was like this. You would say that this corresponded to asymptotically flat space-time. You wouldn't be worried about it. Gravitational radiation goes through the system, so it comes in here, goes out here, and what you would see afterwards is, of course, flat space. It's still flat space, the gravitational radiation has gone, nothing has happened, except that there is gravitational memory. The simplest example of that is that the position of these satellites will have changed. So instead of looking like this evenly spaced thing, they could be all higgledy-piggledy. So like that. That's gravitational memory. The positions of the satellites have changed. There are more sophisticated forms of gravitational memory. It also influences clocks, and it also influences things like spin, but they're a bit more complicated. But that's the basic physical idea. If you felt mathematical, you probably don't like doing this because it involves F and some horrible mess with asymptotic things. You'd say, well, is there some kind of charge associated with these things that tells you about the positions of these things in space-time? The answer is yes. There are BMS charges. As far as I can tell, this bit is new, which characterize the system. They change under BMS transformation. They aren't very easy to work out, so let me just tell you what the answer to this is, rather than actually go through a long derivation. So suppose that you started off with a metric at null infinity g, and after a BMS transformation, you ended up with g plus h. This is how you construct the charges. The charge is an integral over the two-sphere at infinity at some fixed u over some expression that looks like h, the perturbation of the metric, times del A of phi minus phi del A of h. Oh, I'm sorry, I don't want to do that. No, I think I do want to do that. Where phi is the gauge transformation, so it's a metric. I'm going to put this in inverted commas because it involves all kinds of other things. Just a pure gauge transformation generated by a BMS transformation. Let's put charge in brackets here. I've written it this way because it's a very complicated expression that involves lots of tensor indices and covariant derivatives. It's too complicated to write down, and it won't help you. It turns out that this object can be turned into a surface integral. So I should say this is over some space-like surface. Getting a bit ahead of myself. So this thing can be turned into a surface integral at infinity.
If you change the u, the charge is the same?
Yes, because this is a conserved current. Yeah. So let's call this JBMS. That means you can turn it into a charge So you've discovered a whole collection of extra charges that space-time has. Psi, if you remember, involved an arbitrary real function on the two-sphere, so it can be described in terms of spherical harmonics. There are an infinite number of those things. This object, which we can call QBMS, it comes with a psi, means you've specified an F. There will be an infinite number of them. And what this expression tells you is what is the change in the charge associated with psi as you go from G to G plus H. So this is a nice infinitesimal expression that tells you how the charges change between, say, here and here. So we discovered a whole collection of conserved gravitational charges. Of course, if we're just dealing with an asymptotically flat space-time, which is what I drew here, and sort of hoodwinked you into believing that there was nothing else going on, that would be fine. But in a black hole space-time, the situation is slightly different. Let me just do this infinitesimally. So suppose you had a black hole space-time. I won't draw the evaporation process because it's kind of too complicated. You have a situation like that, and suppose we're interested in what happens at Scri plus over there. If you construct a space-like surface, as we sort of did here, then of course it will start off moving in this direction, but you'll come to the horizon. What happens there? It turns out that the horizon also has BMS symmetries. As far as I can tell, this is also new. There are some technical assumptions that go into this bit, but let's suppose we're just talking about a horizon in sort of the usual kind of black hole space-times, so that the metric near the horizon looks something like this. It will look something like ds squared is equal to minus some potential, and then there will be a null coordinate running up and down this horizon, which will be an advanced time coordinate v, the u dv squared. There will be a minus e to the 2 beta dv dr. R will be a radial coordinate, and then there will be some term which describes the geometry of the horizon itself, dxa minus wa dv, dxb wb dv. Any metric can be written in that form as long as u, g, beta, and w are functions of the coordinates. But on the horizon, so u, beta, g, w are in general arbitrary functions. This metric will have no symmetries at all. But on the horizon, u equals w equals 0. So you can ask yourself, are there BMS transformations on the horizon? The answer is yes. Let me just write them down for you. All we have to do is to find the appropriate vector field which generates the transformations, and it works exactly the same way as it did at infinity. There is a vector field psi, which is some function of z and, well, let's call it xa, the coordinates, spatial coordinates on the horizon, d by dv, plus, and then two other terms, an integral from r horizon to wherever you are, dr prime, minus wb db of f, dr prime, and then there's another d by dr, sorry, and then there's another extra term, plus integral from the horizon to wherever you want to be, dr prime, minus a, what do I call this? GAB, dA of f, d by dxb. So there's a vector field which generates symmetries on the horizon. That means there are an infinite number of charges associated with the horizon.
How do you measure this?
You can do satellite type experiments like you did with the other ones. So you can throw dust in or something like that, watch what happens to it. Let me point out before we go any further that this is a classical calculation. So what we have done is we have discovered that if, instead of thinking about dead black holes and what happens to them if they're stationary, and you ask what happens at I0, you find instead, if you consider dynamical black holes, an infinite number of charges which have conservation laws associated with them, which are defined on the horizon. The hope is that these charges can describe all of the information associated with initial state. That's the basic content of what we have done so far. Of course, you need to do a whole lot more than this. First of all, I only did perturbation theory. You should be doing an exact calculation going from somewhere down here to somewhere up after the black hole has evaporated, and you need to prove that it works there. I don't think there's much doubt about that. You also need to do a quantum mechanical version of this calculation. This is entirely classical. What you have to do is to show that the Hawking radiation contains the information associated with these charges. When I gave this talk on Tuesday, or at least a version of it, Stephen Hawking put his hand up and said, "Can you calculate the entropy of the black hole by this method?" Well, he should have known better. I think he was teasing. The answer is yes, in principle, because you have an idea of the number of states that are involved in describing the black hole. They're given by the BMS charges. So in principle, you ought to be able to do that. In response to his challenge, I tried yesterday. I did not succeed, otherwise I'd be telling you about it. I will keep trying. It's early days. You might say, how could this possibly work? Because you found a collection of charges, but suppose, for example, you made a black hole out of baryons and compared it to a black hole made out of antibaryons. You would say that those had different methods of formation, but there's absolutely nothing in what I have done that tells you anything about whether something is made of baryons or antibaryons. That I do have an answer for. It's really quite simple. You have to believe in string theory, otherwise this doesn't work. But baryon number is associated with a global symmetry. Global symmetries cannot really be described by this method, only local symmetries. But in string theory, there are no global symmetries, only local symmetries. You might say, well, of course, you've just described the gravitational field, but other things have long-range fields like this. And indeed, that's true. There is an analogous situation with electromagnetism, where electromagnetism could be described as having a collection of charges also associated with radiation. That also does not appear to be in classical books like Jackson, but it's something that you can do. And then if you're really mischievous, you would say, well, one of the biggest problems in black hole physics, apart from the information paradox, is black hole complementarity. Black hole complementarity basically says, if you are an observer sitting outside the black hole, you will see stuff fall in, happily, and you will see Hawking radiation going out to infinity. That's really what we have described. But an observer freely falling into the black hole will see absolutely nothing. Now, clearly, one has absolutely no control over that here. But nevertheless, it was a question I was asked on Tuesday, and here is my answer to it. Either, you have to make a choice here. There are two possible answers. One is palatable, and one is rather radical. The first one is, simple one, is that they are in fact just different descriptions of the same phenomenon that we have not understood the nature of quantum gravity being rather subtle. So Gerard 't Hooft gave a talk on Monday where he described a few things that look a bit like that, although you could quarrel with his details. But possibility 2 is simply that the nature of reality is not as objective as you think. Different observers see different things. There's absolutely nothing wrong with that. When I said that on Tuesday, everyone thought I was joking, but I wasn't. So I'll stop there. Thank you.